today I chose a very, it's going to be fast actually, and very light topic today. No math, no, nothing, difficult to understand. Because the last 2 days were really hard. To understand. So let's talk about quantum cryptography. I don't know how much you know about these things. About what does mean cryptography, but it has been a while. We are worried about cryptography. Historically, we have the first register of cryptography in this 1900 BC, where the guys used non-standard hieroglyphs. We don't know exactly why they did this, but they used these things. Maybe just for amusement, but nobody knows exactly. And then we have some clay tables in Mesopotamia, they were used to actually hide information, hide messages. And then Hebrew scholars made a simple substitution of letters of the alphabet. Ciphers was the first ones serious attempt to do this. And then we have the modern cryptographic area, when this guy, and this is the entire name of this guy. Yeah, it's known as Al-Kindi, but this guy is an Arabic mathematician that published this book with the first serious attempt to do cryptography in a mathematical sense. And then the first one was Caesar cipher. This was some sort of cryptography was used everywhere in the world, like in Kama Sutra. They have cryptographic things there because the women could not talk freely about those things, so they used cryptographic codes for the women to talk about. So we have this entire seed. This is very easy, the Caesar cipher, but worked for several years. We have the alphabet, and then we just displace it. I just pick up A, B, C, D and put in the end of the alphabet. Just displace it. Okay. So we have the cipher alphabet, and we have the original one. So it's very easy. You have a sentence like this, and you just pick up the letter here, which is the original one, and replace it by the cipher one. So you have the cipher sentence. This worked very well for many years, actually, because it's very hard for you to understand what is really going to happen here. But there is a simple way to break this thing. Very simple way to break this thing. That was covered by a mathematician, an Arabic mathematician, actually. And the way to do this is that if you have a huge amount of message, a very huge text, what happens is that the frequency of each one of these letters is different for every alphabet, for every language. That is a frequency this way. This is the example of the frequency in a huge text of the letters in English. So if you pick up a book in English, the frequency of the letters will be like this. So you see that they are all different. So if you have a single message like this, then you cannot decipher this. It's very hard because you cannot count the frequency here. But if you have many messages, then you can. Then you can, because you can use probability theory to describe this thing, and then you understand what's happening here. Because if the most probable letter in English is the letter E, so if you pick up a thing like this, the letter E will appear as I. So in the cipher message, the most probable one will be the letter I, and you know that the thing is E, and you can simply decipher the text. That was one of the first known breaking of cryptographic codes that we have knowledge about. And this is very nice because you're using mathematics to do this. Actually, probability theory to understand the things and break things out. And that's what's happening today. We want to use quantum mechanics exactly because, in principle, Well, not even in principle, actually. Nobody proved that it is in principle. But as far as we know, the codes, cryptographic codes built upon quantum mechanics, relying on quantum mechanics, cannot be broken. But nobody proved this yet. I think that nobody proved that quantum algorithms can really outperform classical algorithms. Nobody proved this, no? We know that we have quantum algorithms that can perform much, much better than the best known classical algorithm, but, I mean, this doesn't forbid someone to discover a classical algorithm that does the same job. Yep. We cannot prove this. This is actually true. But this cryptographic thing is very nice. I mean, and it's curious because the entire history of human beings, all of the societies searched for hiding messages. All of them. And of course, we're talking about the Arabic guys because the math there was Mesopotamia and things like this was the math is where the place in the world where the math is more evolved. So that's why these things were created there. The Roman Empire and things like this. And then this French guy, now in the much earlier now, much later, this French guy invented this cipher code, which means that he puts the alphabet here, the original alphabet, and the original alphabet here. That's the alphabet in English. And then in every one of the columns, you just place one letter, the alphabet. So it just displays by one letter. So it starts with the A, it starts with Z, and end up with Z here. So that's okay, this is just table, but how do you... The idea of this guy was to break this thing. I mean, to break down the cryptography, the frequency analysis of the text. So how did they do this? Simply choose a key to do this thing. And then let us pick up the same table, but then we choose this key as quantum. That's the key that we use to encode the thing. That's the basis of the cryptography that you have today, a key. And the biggest problem that you have today is to secure, distribute this key. That's the biggest problem that you have, and that's where quantum mechanics get into, to provide a secure way to distribute this guy. Why? Because how do we use this key in this context? It's very simple. You just choose we have Q, U, A, N, T, and M letters. You just choose the alphabet that starts with these letters. So Q, U, M, N, A, and mark them. And then we have a sentence, every sentence, every word. And let us say that we have the qubit word. So qubit word starts with Q. I have the Q and pick up the Q here. It's G. Because I use the first letter of the key. Here I use the key, and here I use the qubit. The second, because qubit, and then I use the key here. And then you associate this guy with the alphabet of this guy. This guy, oh, this was not a very clever choice, but letter B with the alphabet starting with the A. So letter B here with the alphabet start with A, which is this one. Oh, it's B. It's the same letter. But then you can have the same letter mapped to the same letter, to different letters, sorry. And then you break down the frequency analysis. That was the idea of the French guy. I don't remember the first name of this guy, but that was the idea of this guy. So this is a very simple cryptographic thing that took a long time to be broken. actually, but there are algorithms that can break this thing today. I mean, it's not that difficult because you have a very, very, very nice pattern here. So the mathematicians were able to break this thing. And then this is a very famous one. I mean, this is a very serious. I think this was the first serious use of a cryptographic thing. This is a real machine in a museum. I think that's Berlin. That picture was taken. This is the Enigma. The Enigma, the guy simply typed it here, and this machine simply shuffled the letters of the alphabet according to some algorithm, some key that changed every day. And then, while you're typing here, some lights appear here. And the other guy marked these lights. This is the encrypted message. So the other guy that is getting the message must know the algorithm that's here because it changes every day, and the key. Otherwise, he cannot decipher. So this was used by the Nazi Empire during the World War II. And it was extremely well succeeded. And they developed this thing a bunch and advanced a bunch in this technology. This was extremely hard to break until three Polish guys break Enigma for the first time. They break in 1930 something. They break this code, but even though it was difficult to make the computations and then it came the famous Alan Turing, that built a machine that was able to break this thing easily. And then they deciphered the codes of the Nazis, and this was fundamental actually for the Allies to win the war. Because cryptographic messages are extremely strategic, especially for war. So this is one of the most successful implementations of a cryptographic thing. Unfortunately, it was used for the wrong reasons, but anyway, we are like this. Today we have, of course, we know some things that are being developed in this field, but most of them we don't know because there are many private companies that are working in quantum cryptography today, and these guys are being funded by the army or by banks, the financial market. And these guys don't publish papers for obvious reasons. So we actually don't know what we have today. Probably we are much more advanced than we understand it today as quantum cryptography, but I don't know. Maybe if the third war escalates now, we will have an idea what we actually have for military purposes. Yep. I hope not, but things are not that well today. So let us hope that we don't need this thing. But for bankers, this is extremely important, especially if you have a quantum computer. The way we when I go to the bank and put my card there, the bank encrypted all my data and send it to the central. The central decrypted and say this is okay. So they have a key that we could break. It's a huge number, and it's based on the factorization of this number into prime numbers, into its prime factors. This is extremely hard problem to solve, but with a quantum computer, Shor algorithm, we can do this. But we don't have a quantum computer that's able to break this size of number today. But probably we will have in a near time. Then we need to develop a quantum cryptographic thing in order for the bank it doesn't have to change the key every second. That's the problem. The way we can break it using huge classical computers, but it takes months. So the bank just wait for 6 months and change the key. It's over. That's the problem. But with quantum computer, it takes a few minutes. And this would turn impossible the communication between the bank and the clients. So we need. That's why the banks are extremely involved in the development of this thing. A friend of mine has a company of this in Chile, and they just got from JP Morgan $1 million to develop cryptography. I mean, well, $1 million for the bank with JP Morgan is basically nothing. It's, pocket money. But for a scientist, that you can use it freely, that's amazing. That's amazing. But they are actually investing a lot of money in these things, all over the world. So, one-time pad. This is very nice thing. We have the text. This is the word. That's the binary sequence for the word qubit in ASCII2 code. Okay. So that's the first letter. That's why I split it here. That's the Q. That's the U. That's the B, and so on, so forth. So, and then we have a key. This thing I just generated a 40 length random binary string. And then you make binary addition with the key. So 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 0, is 1, 1 plus 1 is 0, and so on and so forth. So that's the encoded sequence. I tried to decode it, but it gave me a bunch of strange characters. I know that this guy is the hat symbol, this guy is the capital M letter, but the other ones here are strange symbols. Me ask, okay, that's why I didn't put it here, because I didn't find the LaTeX comedy for these symbols. So that, and then you see that if you add up this guy with this guy, you get this with binary addition. That's the idea of using quantum keys or keys to decode things. So this guy is public. I mean, you just send it. This guy is public, sorry. This guy is public. You just, you put whatever you want, you publish in the journal. But the key must be holding just by the guy that is sending the message and by the guy that's decoding the message. Because if anyone has the key, he can decipher the message. And the messages are being sent over classical channels of communication that can be intercepted. And the guy have the message, the encoded message, but if he doesn't have the key, if this is really random, and that's the important thing, if this guy is random, then this guy is random. There is no way, because this is addition, binary addition, so if this guy is not random, because it's a specific sequence that gives you the content of the message. But if this guy is random, this guy is random. So for anyone that doesn't have the key, but got the message, it means nothing. It's just a bunch of random numbers without no information. So the huge problem here is guarantee that this key is known only by the persons that are involved, should be involved in the communication. Is key. In the case of banks, just in the ATM machine and the central of the bank. Just that, because if anyone else has the key, they can decodify the message and take the information, and that's a problem. The problem is that today this is encoded, this key is based not in a number like this, but on a much huger than this. And then the key is the prime factors of the number, which is a very hard problem to solve for big numbers. So these rely on the lack of computational ability, the security of the key today, of the key distribution today. But these will be beaten very, very soon. And then we need better ways to do this, because in quantum mechanics we can decipher this code, and that's it. So quantum mechanics provides us a problem, a way to solve this. as far as we know, because quantum states cannot be perfectly distinguishable. That was the idea by Charles Bennett and Gilles Brassard in 1984 to put forward the BBH4, what's known today as BBH4 protocol. They simply use the fact that we cannot distinguish between non-orthogonal states. And nobody can, actually. So the properties of quantum mechanics provides us a way to distribute these guys. That's the problem of quantum cryptography, actually, is key distribution. The rest is easy. So that's BB84 protocol that was published in this paper here. And actually, it was presented in a conference. So this is Charles Bennett and this is Gilles Brassard. They published this in 1984, and the protocol is known today as BB84 protocol. There are several others and several improvements of these guys, but this was the first one. And then we will discuss the idea of this guy here. And this is a very clever solution for the problem. And I think that the most known, most used today is the one published by Eckert, Arthur Eckert, in 1992 or 4, something like this. But, okay, this was the first one, and it's very clever, the idea. I don't know how much you know about this, but it's based on Alice and Bob can communicate over a public classical channel. I mean, they can use whatever channel they want you to send over the messages. But they have access. These guys, Alice and Bob. I mean, I think that they must be very rich because they have access to quantum channels. I mean, at will. So this is expensive, but let us assume that they have money to buy the quantum channels that they need. And there is this girl here, which is Eve, that tries to intercept the message and tries to intercept the communication, but intercept in a way that she can read the message. And that's what Alice and Bob wants to avoid. And also there is noise into the channel that corrupted the message. So they want to avoid these things also. But how to do this with quantum mechanics? In quantum mechanics, Alice and Bob just choose the following code. This is BB84 communication. They choose two bases. The computational base, 0 and 1, which we call Psi00 and Psi10. And they choose the other base that's diagonal to this guy. But note, one important thing in this base is not, I mean, these bases are not picked up in a random way. If you measure any one of these states into the other bases, the outcome is completely random. So that's what we call mutually unbiased bases. Because if Alice codified the bit in these bases, and I try to measure here, the outcomes will be completely random for me. So that's why unbiased is used. That's very important. This is a property that you have in quantum mechanics, because we cannot distinguish this guy from any one of these guys. There is no way to do this. In classical physics, any one of the states is perfectly distinguishable from any other one. In quantum mechanics, this doesn't happen. And these labels were chosen in a specific way that the second label labels the basis, and the first one labels the qubit, the bit that's being sent. Okay, so we have 0 to describe these computational bases, and we have 1 here to describe the diagonal base, Okay, so that's the important thing, and that we have 0 and 1 for the bits that Alice will encode. So how do we do this? Alice generates a random sequence, 2 random sequences. One for the bits that she wants to transmit, that's the information X, she wants to send to Bob. And the other one is the choice of the base. So the choice of the base is that in Alice wants to send one bit. She chooses one bit randomly because we don't care about what Alice is sending. I mean, we simply don't care. This usually will be not random, it's a message, but since we don't care about what's the content of the message, we simply say that Alice chooses this randomly. And we don't care about what's being sent. This must be random, truly random number. Because if every bit that Alice is sending over, Alice chooses a randomly between these two bases for qualifying the bit, that bit. And then with these things, Alice generates this sequence of states. This is not tensor product state. It's just a sequence of states. At each run of the thing, Alice will send one of these states over the quantum channel. Because this state is a qubit. Alice sends a qubit to Bob. So, and the qubit, this guy codifies the basis that Alice chooses, and this guy codifies the bit that Alice encoded in that base. Okay? And then Alice sends this qubit over Bob, over the quantum channel to Bob. So, again, she is the bit, and Y is the choice of the base. These two things go away to Bob. And then what Bob does. Let us assume that the protocol is perfect and there is no weave. So if Alice sends one of these guys, Bob gets exactly the same guy. Because, I mean, there is no noise, there is nothing there. Bob gets exactly the same guy. And then Bob generates a random sequence of this guy. I mean, Y bar. And measures its IQ bit, the bit that he got, in these bases. So these guys, is a sequence of random numbers generated by Bob, and according to these random numbers, which is 0 or 1, he chooses the base to make the measurement of qubit. And he gets some outcome, which is X bar. Since there is no noise, this is the guess that Bob has about Alice's choice of the base. And this is the guess that Bob has about develop the bit that Alice codified there. So this is the outcome, the sequence of outcome. And we see that if this guy is equal to this guy, then X bar must be equal to X, because they are measuring this in the same base. Since this is a pure state, the result is perfectly, the outcome will be this X, this bit, with the probability 1. There is no way. So, but Alice doesn't know what are Bob's choice, and also Bob doesn't know what Alice chooses for this thing. These are completely random. So what they do in the end, they write to Correio and publish the choices of the base. It will be expensive to publish a big choice there, but I mean, they are rich, they can pay for this. But they simply publish these guys. And then they have the strings, but not the results, not the outcomes of the result. They just have the strings there. And then they compare. They discard all the bits for which these guys are different. You see, they know their choices of a basis in the sequence. They look for those one that are equal, they have the same choice, they made the same choice, which is absolutely random, the position of these guys, because they have two random sequences. So the positions of the coincidence there will be absolutely random. And then nobody knows these guys. You see, only Bob knows X bar, and only Alice knows X. Because these things were never sent away to anybody. They are local things. No one else have access to this thing. The only thing that they have access to the choice of is the message, the qubit, that the Eve can simply pick up the qubit, but this is a different problem. And they have access to the random string of choices of bases. Just this. But they don't know which bases we're talking about. And nobody knows anything else. Nobody knows the result of the thing. So this, if I have a big sequence of length n, this will decrease the sequence by 2. Because on average, half of the times they will be wrong. Because the 2 sequences are random and you have half a probability to have each one of them, so half of the time they will be wrong. The remaining strings are identical. The remainder, that x bar and x will be exactly equal. Then they use this thing as the key. They have a perfectly key, local key, that no one else has access. There is no way, unless one of them give away the key. But otherwise, these are perfectly random, a perfect sequence of random numbers. But then comes noise. Comes noise and comes Eve. What happens if Eve tries to... Well, noise will make error here. We'll talk about in a little bit, but what happens if Eve tries to intercept the qubit? The qubit is what is being sent from Alice over Bob. If Alice picks up the qubit, Alice doesn't know which base is there, which base Alice chooses for quantifying the qubit. If she makes a measurement, what happens is get 0 or 1. But the 0 or 1 for her is, if she doesn't know which basis Alice chooses, this is random for her. So it doesn't, Eve cannot simply measure this thing. Because you can think, no, Alice measure the thing and prepare another qubit and send over. Well, this will be random for Bob. This will be interpreted like noisy for Bob. Because the thing is being corrupted in the middle. So they detected this by changing the probabilities of detecting what they want. So when they publish the keys, the public key, they will see that the bits are different. Even if they choose the same base, the bits are different. And if you compute the probabilities will go to 1 over 4. So 25% of the bits will be wrong. Then they say, look, somebody is getting into the communication. And so we need to stop the communication and make better channels. Otherwise we cannot do this. But I say, no, Eve can use other techniques. But there are no way to do this because there is no way to get the information from an unknown state, which is the case for Eve. The only person that really knows the state is Alice. Not even Bob knows the state. And then if Eve tries to I mean, we cannot clone information. We cannot make 2 copies of a state that we don't know the state. That's because of the linearity of quantum mechanics. And that's why Eve cannot do anything. And if Eve tries to do things, he can measure, he can try to send over qubits, but then 25% of the bits, when this choice when this choice is equal, 25% of these times, this guy will be different from this guy. And then Alice and Bob knows exactly, look, we don't have we have someone is trying to get information in the middle of the thing. Or there is too much noise that's corrupting too much our communication system, and we cannot communicate with this because we cannot establish a security key for this. But then to know this, they have to know this guy and this guy. Otherwise, how can they compare if the choices are the same? This they know, it's published in the journal. But these results are not published, and they cannot send the result to Alice. Alice cannot send this string to Bob. Otherwise, it's classical communication, everything is over. How they do this? They pick up half of the message, half of the results, in specific positions, random positions, and publish again in the journal. They just publish it there. Send it to El Correo, he publish it, everything. And then they compare the things. Of course, they have to throw away this thing because this is public, they cannot use for communication. They compare these two sequences that they have there. And see that they estimate two things. Using these, they can estimate the level of noise that you have in the channel. And the level of noise should be small. I think that the best thing that we know today, that we use today, is about 11%. So 11% of these two sequences are not equal. If you go above this, things starts being more complicated, you cannot establish communication. They're trying to get down this level even more. But if you have a 20, 25%, then you know that someone is trying to look at your communication. And then they simply stop everything and establish new channels and start all over again. And so if you have a huge number of element of bases, you can discard half of the sequence here, and still you have n over 4 numbers, bits in your string. That's the key. If n is huge, that doesn't matter. You can do whatever you want with this thing, and that's the way they do this. And then there is a way that I'll not talk about to correct these remaining errors. But this is classical. Is a classical thing that they use to correct using classical error correction. They can use, by knowing the level of the noise, they can use it to amplify the randomness of the key and to decrease the level of noise that they have locally without publishing the keys. And they can do this locally by classical error correction techniques that I don't understand what exactly they do there. But I mean, there are many very well-known advanced algorithms to do this thing in a classical computer locally. They don't need to communicate to do this, and this is really nice. So we can actually use the fact that we cannot distinguish between bases, between distinct bases or distinct states in quantum mechanics in order to make a quantum cryptographic key distribution. So once you have established a key that's known to be secure, nobody proved that this can be broken. As far as you know, nobody published anything, or at least nobody published anything. We don't know if they break this, but publicly, nobody broke this code until today. It's not known, but it's not proven that we cannot do. I mean, maybe there is a strategy to do this, but it's hardly difficult because the keys are established locally. The key doesn't go to one place to another. They don't need to communicate the key. The key, because of the properties of quantum mechanics, the key are established locally and guarantee that they are identical. So that's amazing in quantum mechanics. That's really amazing. This is a private simplification that I was talking about. This is the I don't know what exactly they do here, but they do this in for many years now in classical error correction by estimating the error that they have in this holds for quantum computer, for classical computation, or for classical communication, whatever. This is a sort of error correction that I don't know how it works, but they call it, if anyone is interested, this is called a private simplification. It's purely classical. I mean, you don't have to do anything, and you don't have to communicate to do this. You just need to understand the levels of noise that you have. And then with this, you can actually establish a security key distribution protocol. And this is the Banerjee and Brassard discovered in 1984. just a little bit before Eckert published his famous paper on this thing, Arthur Eckert. And well, as I promised you, today was very easy because the last days were heavy. And guys, I will finish it here today. Very easy talk, very smooth, just a last talk. I was thinking to talk about simulation of fermionic things, but this is very hard. I mean, it's exhausting, and I think that you are already exhausted. So, if anyone wants to talk about this other topic, I'll be here the entire week. So just talk to me, and it would be a pleasure to discuss with you algorithm for simulating quantum systems that I developed with Mikkel here, and it's a very nice one. But he uses graph theory and things like this, so it's better not to push too much the math here. And that's all, folks. Thank you very much.